afternoon. My name is Grzegorz Kisiewicz and I have the pleasure to represent faculty on non-ferrous metals at IGH University of Science and Technology in Poland. Today's presentation was prepared by me and Dr. Artur Kawecki, and the scope of the presentation consists of copper and copper alloys in railway systems. At the beginning, please see a plan of the presentation, which includes a short historical background at the beginning of the presentation and a general description of European railway system, including supply systems across Europe. Next, I will be describing the construction of typical overhead railway system with particular consideration to elements made from copper and copper alloys. One of the most important components of overhead railway systems are contact wires, and therefore I will be speaking in details about different types of contact wires, cooperation of contact wires with overhead equipment and with pantograph. I will also describe material used for contact wires, production technology, and research and development works that are currently ongoing in that subject. At the end, I will shortly describe details of railway overhead equipment, which will consist of materials description, problems existing, and R&D works done on both new materials for the equipment and new production technologies. Okay, let's start from the short historical overview of global railway development. First, steam vehicle, which can be treated as a prototype of locomotive, was developed by a Frenchman, N.J. Quignot, and was running on macadam roads with the maximum speed of 4 km per hour. Sometime later, English engineer Richard Trevithick was the first man to develop steam engines into vehicles carrying passengers. The first of these were for use on roads, but in 1804 he built the first steam engine that moved on rails. The Stockton and Darlington Railway opened on 27th of September 1825. It was designed, built and driven by Stevenson, and a locomotive hauled an 80-ton load of coal and flour 9 miles, which is approximately 15 kilometers, in 2 hours, reaching a speed of 24 miles per hour on one stretch. The first purpose-built passenger car, named Experiment, was attached and carried dignitaries on the opening journey. It was the first time passenger traffic had been run on a steam locomotive railway in the world. 1879, it was a year when Werner von Siemens presented a Berlin exhibition at first locomotive with electrical engine. This date is considered as the beginning of railway, trolleybus and tram electrification, which started 2 years later in 1881 and lasted till the beginning of 20th century. 64 years later, after continuous development of railway system all around the world, in Japan the first so-called speed railway line was opened between Tokyo and Osaka. Shinkansen locomotives set a world record of railway speed at 300 kilometers per hour. 24 years later, ICE train set a new world record with the speed of 46.9 kilometers per hour on Würzburg-Fulda route. Only 2 years later, speed record was broken again by TGV, which reached 515.3 kilometers per hour. As today, we have 2 speed records standing, one for traditional railway train and the other one for magnetic train. World speed record for TGV 150 traditional railway system was set in 2007 at 574.8 kilometers per hour, and Shinkansen magnetic railway in 2003 reached 581 kilometers per hour, which is the highest speed of commercially used railway till today. Typically, in everyday use, this magnetic train goes with the speed of 400 kilometers per hour. On the next slide, a Europe map was presented showing with various colors different countries and regions in countries that are using different railway systems. by the means of type of current and voltage of the line. The most popular for DC current are lines with 1.5 kilowatts and 3 kilowatts. Systems with 1.5 kilowatts are in total 8% of all electrified railway length, and 3 kilowatts about 35 of electrical railway lines. As it is for AC current, the most popular is 25 kilowatts, which is about 41% of all railway transport, which is pretty high. Of course, the type of the line and the amount of voltage determines individual conditions of each railway line. I will be speaking in details about those differences as function of needed material properties later. Exemplary railway traction system, which you can see on the screen, consists of railway tracks, which most of the time are built from steel rails and concrete sleepers. Next, we can see two different types of supporting structures. A single pole on the left-hand part of the slide, designed to sustain overhead traction line above one or maximally two tracks. And on the right-hand part of the slide, there is a gate construction which is supposed to hold overhead traction above more than two railway tracks. Actually, these constructions can have length up to 40 or 50 meters, holding railway traction above 8 or even 10 tracks. From the point of view of copper and copper alloys, the most important components in overhead railway equipment showed in few examples, like, for example, a dropper, which is here, and a wire connector, which joins two parallel contact wires. We have also catenary and contact wires, which are shown on the slide. Both catenary and contact wires were historically made from pure copper, but nowadays they are made from low-alloyed copper alloys, and which are more and more popular. As it is for overhead traction equipment, these elements were historically made most often from aluminum bronzes and from brasses, but nowadays also new materials are being developed to increase the electrical conductivity and mechanical properties of those elements. Typical geometry of contact wire has two regions which were marked with blue and white color. The upper part of the trolley wire, marked with blue, is responsible for good cooperation with overhead traction equipment, and the bottom part of cross-section is responsible for cooperation with contact wire. Also, the European standards are allowing the 25% of wear during the usage of contact wire. When wear will be higher, the contact wire should be replaced by a new product. Abrasive wear of the contact wire comes directly from its continuous contact with the pantograph of moving train. During the ride, pantograph slides on the bottom part of the contact wire, which causes the abrasion of both pantograph sleeper and contact wire. Pantograph sleepers are made from carbon copper composites, and they are designed to wear much faster than contact wires because obviously they are much easier to replace, and they are of course much cheaper. Cooperation of trolley wire and overhead traction equipment is explained in the following slide. You can see a 3D model of contact wire and contact wire holder in close cooperation. We can say that this cooperation is a function of three main parameters, which are material of both components, geometry of both components, and applied feed force. Arms of wire holder should have the same geometry as rows in upper part of the contact wire, and both of them should be made with highest possible precision. When a good contact between trolley wire and holder occurs, a feed force is distributed evenly at entire surface of contact wire rows. In other case, shown on the right, where contact is more of a point contact than a contact at entire surface, a feed force is applied locally, which causes to lower the sliding force to increase of contact resistance, which also results in the increase of working temperature of the wire and may finally cause the damage of both elements as a result of partial melting. A not proper or bad cooperation of contact wire and wire holder may be the result of many different defects of both of the elements. Examples of those defects are shown in the presented pictures. We can see that inaccuracy in holder geometry may cause the non-uniform wear of contact wire, and as mentioned before, a point contact between contact wire and holder may be the cause of further breaks of the contact wires, which may significantly increase operational costs of the line. The European standards are showing three main types of contact wires. The geometry of contact wires with the name starting from the letter A, starting from the letter B, which actually has two types, BC and BF. Generally, the geometry is more or less the same. In the differences between A and B is in distance between the rows of the wire, and difference between BC and BF is in the bottom part of the wire. In BF construction, the bottom part of the wire is flattened in order to achieve a better contact with pantograph. In the same standards, we can find information about possible copper alloys that can be used to produce contact wires. In general, we have pure copper, copper with addition of silver, which is at this point the most popular solution. Also copper with addition of magnesium, also very popular solution for AC supply system with higher traveling speeds. And copper with cadmium, which is kind of rarely used, as well as copper with tin. Pure copper and copper-silver materials are generally optimal because they have the best current capacity and low electrical losses. Both materials have similar electrical conductivity, but extremely different operational properties like wearing and heat resistance, with significantly increases with the addition of silver. Depending on the current supply system and desired speed of train, we can use different contact wires materials. For 3 kilowatts DC current and train speed up to 160 kilometers per hour, the best solution is typical CuETP copper, which has very good electrical conductivity and sufficient mechanical properties. For the same supply system, but increased speed up to 250 kilometers per hour, a copper-silver material is used most of the time, as it has the same level of electrical conductivity as CuETP copper, but it also has increased mechanical properties. The ultimate tensile strength is 40 megapascals higher than in CuETP. For the 25 kilowatt AC current supply system and speeds higher than 250 kilometers per hour, mainly because of the higher used voltage, following Ohm law, we don't need to have a material with highest possible electrical conductivity, but because of the high traveling speed, we need to have a material with high mechanical properties. This is the reason why in those systems the most popular is copper-magnesium alloy with ultimate tensile strength at the level of 420 megapascals and electrical conductivity of more or less 75% of IECS. Of course, copper-silver can be used in this system as well, but it is more expensive due to needed more addition of silver in that alloy. So, we said that with the increase of train speed, we need to have higher mechanical properties as well. This dependency comes directly from the physical phenomena that is present during the sliding contact of pantograph and contact wire. During the locomotive ride, pantograph interacts with contact wire and creates a mechanical, which is a disturbance wave, which travels ahead of the train. This disturbance was marked on the scheme with capital C letter. In general, speed of the train had to be lower than speed of disturbance wave, because when they will be the same, or the disturbance speed will be higher than speed of the train, it may cause the resonance of entire traction line and actually result in damage of entire system. Calculations made and shown on the slide, including the value of the mechanical wave and maximum applied tension, show that ultimate tensile strength of the wires needs to be increased along with the higher speed of the train. Also, which is very important, the minimal ultimate tensile strength is much higher than usual ultimate tensile strength of used material, and this is due to several different factors: safety factor, temperature factor, wear factor, creep factor, factor responsible for different phenomena connected with wind and ice, also connections, clamps and welds, all of them existing in a single line. On the next slide, I've shown three different working hard curves of three different materials, which is CuETP copper, marked with red line, CuAg with 1000 ppm of silver, marked with green color, and also copper magnesium with 0.5 magnesium. Okay, the blue region on the characteristic shows the typical strain of the wire produced today. Also, the train of the speed was shown on the slide, and we can see that starting from the speed of 150 kilometers per hour, we have the minimal ultimate tensile strength at the level of 355 megapascals. And for this example, we clearly see that all included materials are good for this system and for this speed of the train. But of course, we most often use typical CuETP copper in this example. With the increase of the speed of the train, now we have 250 kilometers per hour, the minimum ultimate tensile strength also increases, and calculations shows that this value needs to be at the level of 394 megapascals. And we can see that in this solution and in this speed of the train, this traditional CuETP copper, it's not good enough. The CuAg copper is actually better here and is more often used. We're going higher. We have 300 kilometers per hour, and now we can see that both CuETP and CuAg copper are, from the mechanical point of view, not a good solutions for those speed of the trains. So only copper with magnesium 0.5 will be good here. And the highest speed shown in this presentation, which is 350 kilometers per hour, and minimal ultimate tensile strength is at the level of more or less 500 MPAs, and we can clearly see that none of the materials showed can be used as a contact wire with this traction line. Of course, we can use a copper silver or copper magnesium with FUHR magnesium and silver alloy additions, but of course in this situation we will also have to lower the electrical conductivity of those materials, but actually those materials are being used in these systems. The typical production technology for contact wires is based on the drawing process. Also, with the drawing process, we have some various actions that can be taken to reduce the geometry of base material and to obtain a final trolley wire. In the slide, I've shown a sample production technology with the use of FUHR roller die. So at the beginning, we are drawing the material 3 times with the circular dies, and then we use FUHR roller die to create rows on the material. And at the last step, it's a final drawing system that enables to obtain material with very good and very accurate geometrical dimensions. You can also obtain contact wires with the use of rolling method, which is shown on the screen. We actually, for this process, we need 4 rolls, which are shaping the geometry of the wire. But the most, as I said, the most popular and mostly used method is a pure cold drawing process of copper wire contact. And starting from the base material, we can see a typical strain scheme. And in this method, the rows of the wire are being created partially in every single step of the process. This guarantee the best geometrical parameters of the final product. Also, which is very interesting, for the cold drawing of trolley wires, we need to use special wire dies, which are also shown on the left down corner of the slide. And those dies are complex tools with a red part shown on the scheme, which is responsible for the creation of the rows during the cold drawing process. Because of the high forces existing in the cold drawing process, we also have and see some breaks of the die during the contact wire drawing process, which were shown as an examples on the slide. You can see also on the finite element method calculations that the highest loads and highest pressures are existing directly on the part of the die where the trolley wire rows are being created. And this is the direct effect that causes the breaks of the die during the process. On the next slide, I've shown some studies on materials used for contact wires. We can see different geometries of the wires and different materials. We have copper ETP, copper with 0.1 silver addition, copper with 0.2 magnesium addition, and copper with 0.5 magnesium additions. We can clearly see that the highest mechanical properties have the AC 150, and 150 means that it's a cross section of the wire, 150 square millimeters, and the ultimate tensile strength is 474 megapascals. But of course, in this situation, we have also the lowest electrical conductivity at the level of 40.4 megasiemens per meter. Also, which is very important, and as I said, sometimes during the cooperation of contact wire and holders of contact wires, we have the possibility to interact with higher than usual temperature of the wire. And also the copper with the addition of silver have the higher resistance to thermal effect on this wire. So we need to have a higher temperature that causes the decrease of mechanical properties of the material, which is shown on the characteristic below the screen. At the end of production technology, wires need to be tested in 3 ways. The first one, shown on the right-hand upper part of the corner is a bending test. So we need to bend the material 3 times and see if there are no breaks on the wire. If the test is okay, we're going to the second test, which is making a spring from the wire, and also we need to have 3 spring layers, and we are looking for the possible breaks of the wire, and if it's okay, we also use the third test, and we're seeing if everything is okay on the wire, and after those tests, the material is ready for usage in traditional railway line. All type of equipment are made from different bronzes, and they have relatively good mechanical properties and high corrosion resistance, but they have a very low electrical conductivity. Equipment made of these materials has a number of defects in shape, surface, and internal defects arising from the casting process and the production technology, and also this requires large size of equipment to ensure the strength of the material. It poses the risk of degradation of mechanical properties of the conductive and carrying elements of the line. In the next slide, I've shown some examples of internal shape and surface defects of traditional overhead traction equipment, which may cause to the defect in the catenary existing after the usage, for instance, after 10 years of exploitation of the line. That's why there are also some research and development works being concentrated on the new modern overhead traction equipment made from new materials, of course, still based on copper because of the needed electrical conductivity, good needed electrical conductivity properties. And here we can see the examples of old equipment and new equipment for holder for parallel connections of the trolley wire and catenary, also for dropper contact wire holder and contact wire holder for extraction arms, and some other examples which are shown on the right-hand side of the slide. The modern production technology is also extremely different. In traditional overhead traction equipment, we've used casting technology, and nowadays we first design prototypes and then we test it with the use of PM simulations, and next they are being forged, and this is the newest technology that enables to create elements with very high and very accurate geometrical dimensions, which is, as I said, very important in the means of their cooperation with contact wires. On the next slide, we can see some examples of traditional materials and the new used material, which is copper with the addition of nickel and silicon. And we can see the difference in operational properties for those 3 materials. The copper with nickel and silicon has the highest ultimate tensile strength at the level of 760 megapascals, and also it has the highest electrical conductivity at the level of 28 megasiemenses per meter. So this material is both electrically and mechanically better than traditionally used material, and nowadays most of the new lines and most of the modernized lines use copper with nickel and tin alloys as mandatory for higher speeds of the train. Okay, this is the end of the presentations. I would like to thank you for your attention, and see you